The dynamics of playing pool are complicated, but very interesting to study. Not only do we have collisions of all these multiple particles, which we touched on in particle dynamics, but we also have rotations of the spheres that interact with the friction of the felt and the rails. And so we can put top spin or back spin, which we'll discuss in a moment, but we can also put English, which would be a side spin, and so it comes off the rail or reflects off the rail in different ways. And so this allows us to control the cue ball in important ways so we can set up our shots. Let's talk about the most basic of the ways that you control the cue ball. So the first would be called a follow, and a follow is where you're going to apply an impulse high on the cue ball or above the center of mass, and with that it's going to create a top spin, and then after making contact with the object that you're shooting for, it's going to follow that object. Now similar to that, we would put backspin on an object, and that's called a draw. So after it makes contact with the object, the cue ball will spin backwards and even come back toward you. And in all this, we're interacting with the felt. There's friction with the felt and with the table itself. And so there are even times when you can forcefully apply a backspin, and that'll turn into a follow because of the fact that the friction itself catches up with the linear momentum. So there's all kinds of interesting situations that we can study. And in this example, we're going to be very simple with it. We're going to look at a condition in which we're hitting the cue ball, and we want to find out what we need to do to make the cue ball roll without sliding. So if we hit the cue ball through the center of mass, right through the center of mass, then we're going to be pushing the cue ball without any rotation, and so that'll initially slide. It will eventually turn into a roll, but it's going to slide. And so to make the cue ball roll immediately after the strike, that means we need to hit it with a top spin. And so in this problem, we're applying an impulsive force, Fc, to the cue ball, and it's according to the diagram. So we want to find the height above the center of mass of the cue ball that we need so that the cue ball rolls without slipping immediately after the impulse. So we're applying the impulse at time 1, and at time 2 the cue ball should be rolling, not sliding. So here's our system diagram of our cue ball. Let's define a point C, which will be the location at which the cue is going to strike the cue ball. And so we need to add reference frames to this system. For our inertial reference frame, we'll set the origin at the point of contact, which is located in the inertial reference frame. We'll define E2 along PG, which is the point of contact with the felt, to the center of mass, E3 coming out of the plane, and then E1 being E2 crossed with E3. And then we'll apply body frame to the problem, where we have an origin at the center of mass, and then B2 is the same as E2 when the coordinate theta is equal to 0. B3 is the same as E3 coming out of the page, and then B1 is the cross product of B2 and B3. Our velocity relationship between these reference frames, so B as observed and I, is equal to the scalar omega B in the B3 direction. We also know that the moment of inertia about the center of mass of a sphere is 2/5 mr squared. And we find that in a table. And then also take note that we have two coordinates. We have x, which is the distance from the point of contact to the center of mass, and then we also have theta, which is the angle between the two reference frames. When working with impulse-momentum relationships, we know that we need to have kinematics to the velocity, and then we also need to use our free body diagram to solve for our impulse. So let's start with our free body diagram in this problem. We have our cue ball, and the forces on the cue ball will be the impulsive force, Fc, this is from time 1 to time 2, and then we have the force due to gravity, which is mg in the negative E2 direction. And then we also have the normal force, so this will be N in the E2 direction. This is acting at point P. And then we have a friction force because we have felt on the table. And in this problem, we've stated that the cue ball is to roll without slip. So that means that this friction force is a static friction because there's no slip that's occurring. So we can write this friction force as an unknown scalar in the E1 direction. Note here that this is different than dynamic friction or Coulomb friction that we've used before, in which we have to be very specific about the relative velocity of the cue ball with respect to the table and account for that in our model of the Coulomb friction. So now let's apply our impulse-momentum relationships. The first is our mass times our velocity of g with respect to c as observed in the inertial reference frame at time 2 is equal to the mass multiplied times the velocity of g with respect to c as observed in the inertial reference frame at time 1 plus the impulsive force at c from time 1 to time 2. We solve for our velocity of the center of mass with respect to c, which is inertially fixed. And because this is only translating, because it's rolling, our time derivative of the inertial reference frame will be x in the E1 direction. That's our coordinate that we defined from c to g. And then when we differentiate this in the inertial reference frame, it's x dot E1. This takes care of the term on the left-hand side of the equal sign and the momentum term on the right-hand side, because we can find x dot at t1 and then x dot at t2. And now we turn our attention to the impulsive force, and in this case it's the impulsive force due to all the forces on the body. So when we look at our forces, we have our impulsive force C, we have the force due to gravity, the normal force, and then we have the force due to friction. And so recall that in this impulsive force, we're interested in the forces that are acting over a small period of time and that are very large forces. So here we have constraint forces, and recall that constraint forces don't add or subtract momentum from a system because they're simply constraining. So we have our force due to gravity, and then in this case the constraint that's equal and opposite to that, so those would cancel. We have our impulsive force applied by the cue, and then we also have this static friction. And so what we have here is a relationship between these two where we have a large impulsive force due to the cue and a very small static friction force, which is simply applying the boundary condition to make this roll. So in our impulsive force, we're only going to consider the impulsive force due to the cue. The impulsive force itself, if we plot our force over time, we would see that Fc is going to be very large and acting over a small time period that we'll call delta t, which is t2 minus t1. And so then our impulse from t1 to t2 we can define in vector form as the force c, which is a scalar, multiplied times delta t, and we've drawn it in the E1 direction. So we'll just say that it's acting in the E1 direction because we're trying to shoot our cue ball to the right. We substitute these expressions into our expression for the linear momentum, and from that we get m x dot at t2 is equal to the mass times x dot at t1, and then we'll add to that the force at c delta t. And so these are all acting, so I dropped the E1 direction because we have E1 direction for our impulsive force as well as the E1 direction for our x dot, or our velocity. And now at this stage we can apply both one boundary condition as well as one constraint. Our first boundary condition is that our cue ball starts from rest. And so if the cue ball begins from rest, then x dot at t1 is equal to 0. So the velocity is 0, the speed is 0. This scalar speed is 0, at time it's equal to 1. And then at time is equal to 2, we have another constraint that we can apply, because we know at time 2 we're solving for this so that the ball will be rolling without slip or bounce. And so this is a constraint that we've applied many times. And it's that x dot at time 2, which is our velocity of our center of mass, is equal to, will be the radius multiplied times the angular speed. So it's negative omega b. And the reason why we chose negative is because we've defined our reference frame here with positive b3, and so we want it to roll clockwise, And with a clockwise rotation, this is the opposite direction of how we've defined our coordinate theta. And so with this constraint, our speed at time t2 is equal to negative r omega b, and this is at time t2. And when we substitute our boundary condition and then our constraint into our linear momentum equation, we get negative m r omega b at time t2 is equal to fc delta t. Next we apply our impulse momentum relationship that's rotational, and that's omega b as observed in I at time 2 is equal to omega b as observed in I at time 1 plus 1 over the moment of inertia multiplied times the impulsive moment from time 1 to time 2. We know that the angular velocity of b as observed in I is equal to omega in the b3 direction. So we can simply replace this at time 2 with omega b at time 2, and then omega b is observed in I at time 1 with omega sub b at time 1. This takes care of these two terms, but we can apply a boundary condition because we know that the cue ball is starting from rest. So that means that omega b at time 1 is equal to 0. So now let's deal with our impulsive moment. And this will be due only to the impulsive force that we're considering. So this is the impulsive force of the cue stick hitting the cue ball. And so this will be r of c with respect to g cross with the impulsive force itself, time 1 to time 2. And so when we substitute in this expression, we get negative x in the e1 direction plus h in the e2 direction cross with f sub c delta t, and this is acting in the e1 direction. We evaluate the cross product and get negative h f sub c delta t in the e3 direction. And when we substitute all these pieces into our impulse momentum equation, we get omega b at time t2 in the e3 direction is equal to 0 plus 1 divided by the moment of inertia, I sub g, multiplied by negative h, our force at c, our small time increment delta t in the e3 direction. And then when we substitute in our moment of inertia, we get 2/5 m r squared multiplied times omega b at time t2 is equal to negative h f sub c delta t. So here's our second scalar equation that came from our impulse momentum relationship that's rotational. We combine that with our impulse momentum relationship that's translational, and then we'll be able to solve for the height above the center of mass that we need to apply the cue stick to make it roll. So we have an expression from our linear terms of s sub c delta t, and when we substitute this in, we get 2/5 m r squared omega b at time 2 is equal to h multiplied times negative m r omega b at time 2. So we've got a lot of terms that are going to cancel. Our omegas cancel. We get an r that cancels on the left side with an r on the right side. Our mass cancels and our mass cancels. And then when we solve for h, the height above the center of mass is equal to 2/5 multiplied times the radius. So in summary, what we've done is applied Euler's first law and Euler's second law, but we've done this in a momentum and impulse fashion, in which we were applying an impulse between a specific time 1 to time 2, it's over a small time, and we've applied our constraints, and our constraint was that it rolled without slipping or without bouncing, and then we had our boundary conditions, which it was starting from rest, and then determine the height above the center of mass that we needed simply to make the cue ball roll.